Welcome to this 9th video in the yt-napari tutorial series. In this video I'll be talking about some image segmentation and classification using yt-napari, data loaded from yt-napari, along with some other plugins in the Napari plugin ecosystem. I'll talk through some examples of how you can manually label data that you've loaded in from yt-napari, and then how you can use some other plugins to do labeling instead, and then we will walk through some interactive visualization of data within those labels we've created, as well as how you can go about sampling multiple YT data fields for some interactive plotting within those labels. And then we'll end with setting up a kmeans pipeline a couple different ways, and in this video we will rely on the napari-simpleitk-image-processing plugin, as well as the napari-clusters-plotter. And usual requirements as before, those plugins I mentioned will also be relying on pandas here, which you'll probably already have if you've done a full YT install. And we will be using the yt-tiny cosmology dataset, and probably also the isolated galaxy dataset. Thanks to Chan Zuckerberg Initiative for funding to help make these tutorials possible. So here we are in my terminal window with, I've already activated my yt-napari tutorials environment, and so we're going to start off by installing a few more dependencies here. So let's install our plugins. So we're going to first install the napari-clusters-plotter. And then we've already installed this for the previous video, but let's just do it again just to make sure you all have it. So napari-simpleitk-image-processing. This one will give us a bunch of filters and segmentation methods. The clusters plotter provides some interactive plotting, as well as some kmeans classification as well, and some other clustering methods. But we'll just use the kmeans today from that. But we'll use the interactive plotting a bunch. Okay, so for this video, we're gonna work from a Jupyter notebook. So let's spin that up. Great, so we're gonna start by just importing Napari and opening up a viewer. And I'm actually gonna load the YT data interactively from the GUI rather than using the notebook interface. So let's go ahead and do that. Plugins, yt-napari, YT reader, and we will be using we're going to start with the yt-tiny cosmology final time step there, and we're going to add a number of fields. So we're going to add the enzo density, enzo temperature, so let's bring in the metal density, and so just bring in dark matter density as well, and then we'll do one more. Gas velocity magnitude. And we do want to drop the resolution on this, so we're still going to sample at a resolution that we can see the features pretty well, but this will just speed things up for the video a bit, since I don't want to overwhelm my memory while recording the video and doing the processing. Okay, oops, that should be a 200 there. Okay, so we have our 5 fields we're going to load in, all covering the same region, 0 to 1 code length, and at the same resolution. So let's go ahead and run that. And let me resize my window here. Okay, so we have our 5 image layers here, and oh, you know what? I forgot. Let's actually delete that velocity magnitude. So the velocity magnitude here, we're gonna actually go back and load it in again because I did not want to take the log of that one. Okay, so now we have our velocity magnitude, our dark matter density, which is not defined at every point in the model, and our metal density field, temperature, and density. I'm just going to keep all these in grayscale for now, at least. Great, so labels. So what we want to start off by doing is introducing the labels layer. So the labels layer can be used to select different parts of the image, which you can then use for various filtering and classification algorithms. And so we're going to start off by doing this manually. So we have our viewer handle here, v. So if we take a look at v.layers, we have all the layers that we've loaded in here. And what we're going to do is basically just bin our density field to create some labels that we will then add to the Napari viewer. So let's get started with that. So for that, we're going to want numpy, import numpy as np. And then actually let's pull out our density values. So these are log density values, e.layers, and we can give it the layer name. And if we just, so this will be the Napari image, and let's just pull out the underlying array. And let's just get a sense for the dynamic range of our density field here. Okay, so let's create some bins. So we're gonna create an array that is the bin edges for our label. So these are going to be bins in density, and we'll just go from, let's go from -3 to 5, and so if we have 31 edges, we'll have 30 bins in labels, and so we'll have n labels equals to the number of edges minus 1. And now what we want to do is create a new labels layer. So we're going to have a new layer that's going to be our labels, and we're going to have it be the same size but start off as zeros. So log dense shape. And then we just want to cycle through our bins and assign an integer value everywhere the density falls within those bins. So for the label 1 through so for the label in the range of n labels, we want to find the locations where the density is equal to the or falls within the bin. So let's do the bin left edge is going to be the current value, and then the right edge will be 1 to the right. And then we'll create a density mask. So we want to find the locations where the log density is greater than or equal to the bin left edge and less than bin right edge. And so that's going to be for our current label, that'll be our mask, and then in our new layer we want to set everywhere that we're within the bin, we just want to set it to our identifying integer value. Oh, and I did forget that this should be a integer, so let's redefine that. And let's run that. So now we have our new layer here, same shape as above, but now we have integer values corresponding to all of our bins. So let's add that to Napari. So the viewer add labels. We'll give it the label data, the new layer, and give it a name. Let's call it density labels. So if we go back to our Napari viewer, we now have our density labels array. And as you slide through the third dimension, you can see how the regions falling within the different density bins change. And since we're just binning by density, it just more or less follows the contour of the density field. So once you have these labels, you can do a number of things in order to probe the values of the different image layers within these labels. For example, the measurement tables region properties tool. So you can select any of the fields of interest and then the labels that we want to sample for, and it'll extract a number of different metrics related to the labels. So the intensity is just the value of the field at that point, and then the size and shape position, these are all related to the actual kind of morphology of the labels themselves. So if we hit run, we'll get this properties box that pops up. And so we kind of talked about this in the last video, but all of these values actually get stored as in the properties attribute of the density layer, and so we could go ahead and use some of the visualization tools to actually plot those values. But for now, let's actually pull up this clustering widget. Sorry, plugins, the napari-clusters-plotter, and then we'll pull up the plotting widget. So this is another interactive plotter. One of the nice things about it, so we can select our labels layer where our data is stored, and then select some axes. Actually, before I do that, I'm just going to right click and duplicate that layer just in case I mess things up through this. So these are the max, mean, min, intensity of the density values in our different domains. So let's pick that, and let's just look at the area of each. And hit plot. So what we get here is a scatter plot where the x-axis is the mean intensity, y-axis is the area of the label itself, And actually, let's first let's look at label and mean intensity. So this is just essentially the bins that we set up, right? The number of bins that we wanted, and then how the density increases across those bins. And so if we want to look at how the area changes, how the area relates to the density here, you can get this plot. So the plot isn't super meaningful right now, but one of the nice things about this plotter widget is that you can actually click over here and select points, and it will highlight the points that you've selected, so you can see the spatial distribution nicely. And if you hit this hide not selected, you get just the labels, the corresponding labels in space in the viewer here. And this works in 3D as well, so you can switch to 3D. And as you select points, we are actually just getting the surface layer there, but so sometimes it's a little easier to kind of step through. Okay, so, and this is some pretty useful functionality, but it's a little bit more useful if we can get data from our other image layers into this plot over here on the right. And to do that, we're going to have to manually change some property values. So let's go ahead and delete that for now, close that, and let's delete the old, and then we'll just use the density labels copy, rename that to density labels. Okay, so back in our notebook, what we'll want to do is take a look at our density labels layer. And so this image layer, we can, if we add a properties dictionary to it, we can put some values in this properties dictionary so that it shows up in this Napari clusters-plotter widget. So let's import from collections default dict, and let's create a properties dictionary that just defaults to an empty list, lambda empty list. And now what we want to do is let's create a list that's just the layers that we want to sample. So remember, these are the available layers we have. So we're gonna sample Enso density, but we also want all the others as well. So Enso temperature, Enso metal density, Enso dark matter density, and gas velocity magnitude. Oops. Okay, and now what we want to do is cycle over each of the bins, so each of the labels. So for the label in, we'll just find the unique values of our label layer here. Let's store our current label that we're working with. And then we want to create a label mask. So for this label, these are all the points in the pixels in the three-dimensional array equal to this label. And then we can use that to sample each of these layers. So let's pull out the data, label data. We're going to pull from our Napari viewer layers, the layer name we just created, and then we can pull the data out, and let's just take the mean of our labeled data where this label mask is true. And then store the result, and we'll just be explicit here that it is the mean value. And oops, we want the formatted variable to be the layer name. Great. So now we have this properties dictionary that has our labels as well as the, oops, we need to append the result. Okay, now we have our labels and the corresponding values for each of those. And oops, we can see that our dark matter density actually has some undefined values in it. So let's quickly fix that. So let's move this indexing up, and then the label data, we can take the mean where the label data is finite. And let's reset our properties dictionary. And now those look a bit better. Oh, we actually somehow ended up with unit quantities. That's interesting. In any case, so now we can go ahead and add this new properties dictionary to our density labels. Now we can go back to our Napari viewer, go up to plugins, clusters, plotter, plotter widget, and let's plot some things. So what we have here is a scatter plot of the density values within our labels and the temperature, mean temperature values. And one of the nice things about this plotter is that it is interactive, so that you can click and drag and circle, and it'll show you in blue the highlight, the points that you've, it'll show you the labels spatially that correspond to these values over here. And if you hit this expand for advanced options, you can hide the non-selected clusters, and what you get out is just those that you've selected. And you can go, just click around and select, and it'll just highlight the regions that correspond to that. So we can check out any of the fields that we just added in. At any point you can select and see spatially where these points correspond to. Let's try to switch to 3D view, see how that is. So in this case, these points out here, there's not that many of them. So it's just this little pixel up here versus these that correspond to larger regions. And if you unclick the actual labels layer, you can get a nicer kind of 3D rendering there. And those middle values correspond to some of the filaments. Cool. So a couple other notes. So if you switch to a histogram here, you initially get a 2D histogram. If you instead switch to the same value, let's increase the number of bins here, and then you'll get out a 1D histogram, which you can also sub-select from. Yeah, so that's a nice quick way to manually segment an image into bin labels, and then kind of manually load in the different values from the different image layer channels into the cluster plotter. So one of the nice things about all these Napari plugins is that there are ways to create this labeling layer semi-automatically using various image processing algorithms. So let's delete our density labels here, and let's take a look at some of them. So in tools, there's a number of options here. So all these filtering are kind of standard image processing filters that get applied to the pixel intensity values or similar. So there's Gaussian blurs. These H maximum and minima will restrict the limit. Will apply some limiting to either end of the scales of your images. And what we want to look at are down here in the segmentation options. So there's a number of options here. So this threshold Otsu multiple thresholds is a nice, pretty simple one. So this does a very similar thing where it'll take the image data and bin it into different ranges within that data. This works. It doesn't use fixed bins. It does some analysis of the histogram of the values and kind of distributes the bins according to how it thinks best represents the data based on the intensity of the pixel values. And so if we just go ahead and run that, you'll see we immediately get out this 3D label where generally let's switch to a 2D view, where we immediately get out our, high density filament regions. We can, however, supply a higher number of bins. This multi-Otsu thresholding algorithm, though, does not scale super well. So if you increase this number of thresholds, you really got to decrease the number of bins it uses to build the histogram representing your data. So for our current data, let's increase this to 8 and drop this down to 50. And so this will run in a reasonable amount of time, maybe about 20 seconds or so. And now we have our labels image with a bit more detail because we have a higher number of thresholds, and you can see it pulls out the high density regions in a bit more detail. And now if we want to just take a look at single values of our labels, we can go to measurement tables, region props, and then select the image layer we want to sample, and then the result of our Otsu thresholding. So let's use our density labels, but look at how the temperature changes within those. Actually, let's do the velocity. Run that. And now we're done. So I think that takes a little bit of time, mainly because it's doing these geometric calculations, like convex area, and we have some oddly shaped regions for the algorithms it's using, probably. But oh, I did want to actually show the 3D view of this too. So if you switch to 3D, hit show selected, you can cycle through our segments and actually kind of pull out the finer detail as you go to the labels that cover the higher density fields. Okay, but in any case, let's keep going. So we now have all of our velocity magnitude data stored in our label properties here, and so now we can go back to the plotter, clusters plotter, and look in our results, and now we'll have the intensity of the temperature in the different labels. Well, actually, let's switch those axes. And so we can see that higher labels correspond to higher density. If we select these blue regions, correspond where the density is highest as well. And let's hide the not selected. Yeah, so just like we did before with the manual selection, we could go back and actually, sample each of these fields and add it to the properties dictionary so that it's available here. I'm going to skip that for now, though, and do that with the next thresholding method. So let's get rid of our Otsu. And so one of the other interesting ones that's pretty simple to use is the segmentation labeling tool, the morphological watershed. So what this does is it treats your intensity data like a topographic map, and it fills in pseudo water levels until it finds the boundaries between different domains. And so it's a nice way to do void detection really quickly. So let's just try this. So we're going to do this with our density field. This level here corresponds to the pseudo water level in our watershed exercise. A larger level means more of the local minima are ignored. So let's first drop this to 0.5 and just see what happens. And now we get out our different domains corresponding to our different watersheds. And so these are fairly big domains because our flood level is pretty high compared to the intensity variations within our domain. And so as we drop this and rerun, you'll see that we pull out smaller domains. And let's just keep going. And if we drop the opacity on this layer, you can kind of see more clearly how it corresponds to the underlying density field. And if we try to look in 3D, and click to show selected, you can click through and look at individual watersheds that were detected. And let's do this one more time and get a bunch, just to make the plotting a bit more interesting. Oops, maybe I went too low there. Okay, let's keep it at 0.1. Oh, actually, I bet yeah, okay. So I had gotten that error because I had been adjusting parameters here and then changed it and then tried to use the same parameters and they did not work well. Okay, so now we have a bunch of watersheds. And what we want to do is go back and again, for each of these label domains, find the values for our various fields within those domains. And let me just clear that error message there. Great, so in our layers, we have now our result of morphological watershed, and actually let's quickly rename that to make it a little bit easier to type. Density watershed. Cool, so what we want to do is pull out our watershed labels, density underscore watershed, and let's actually pull out the underlying data here. One nice little feature is that when you pull out the data here and just if you're in a notebook and hit return, it'll actually plot a slice for you using this simple ITK package. Yeah, so each of these are integer values. So just like before, we'll want to loop through all of the possible values and add it to a dictionary. So I think we should be able to just use the same exact code, and I'll just copy paste it down here just for clarity. We'll want to change the label array that we're using here. But otherwise, we want to sample all the same layers, and let's just run that. And now we'll want to add that dictionary we just created to the density watershed properties. And let's head back over to Napari and go back to the clusters plotter widget and density watershed, and we now have all of the mean values for our fields within each of those watersheds. And now we have a bit more of an interesting distribution than before. And again, you can select, circle and select, and it'll select the watersheds corresponding to those regions. Let's hide the non-selected and maybe switch to 3D and see what we got. So that's a pretty big region, so it's kind of hard to see the underlying field, but if we select just a couple, you can start to pull out individual watersheds from the distribution here. And just like before, we can use histogram instead. And pull out just the high velocity regions. And note that because of how we're calculating these characteristics, the mean value is gonna be weighted according to like what is in the watershed here. So there, we could spend some time kind of cleaning that up so that, for example, like these high velocity values are probably encompassing just some of these high density regions where the velocities are high. So those are why those sections are skewing, even though maybe the minimum value is much lower than this. And yeah, cool. So let's deselect that. Yeah, so that's kind of a useful way to quickly kind of segment our our density images, especially for these cosmological simulations where you have the filaments corresponding to high density regions. And so if you want to identify the spaces between them and quickly take a look at how the characteristics might vary, this watershed segmentation is a nice way to do that. And you can then manually update that properties dictionary to include the values for multiple channels. Because you can, also, like before, you can run these measurements properties, but generally they're going to just take in a single image layer and characterize the labels and the single image layer. But it actually would be useful to run this to look at the size of the watershed, especially if you could use it to compare different time steps, for example, in a simulation, to compare how the number of watersheds increases and the relative size and stuff. But we're not going to do that right now, because we're going to move on to some other features. So one of the other parts to this Napari clusters plotter is this clustering widget. So what this allows you to do is, for an image layer where we have properties stored, you can actually run a number of clustering algorithms to characterize those variations. So, for example, you could do a k-means calculation that would take all of your fields, run a k-means clustering, and then in our interactive plotter, you would then be able to look at how the distributions actually, how those k-means distributions correspond to the histograms and scatter plots. So to use this k-means functionality, we're going to do things a little bit differently. We could have used the watershed, but let's do something else just to show some of the other functionality that's possible. So what we're going to do is take our 3D density our image array, and segment it to highlight just the high density regions here. So what we'll start with is this filtering H minima to remove some of the lower density. The value of 4 will pick up our high density regions pretty nicely. And then we want to apply a number of other filters. So first off, we will use a standard threshold on our result layer. And what we get out is a label layer corresponding to those high density regions. And then what we want is for each of these high density regions to be its own label, so that we can look at the variations between them. And so we can do that with this segmentation labeling connected component labeling, and we want to run it on our thresholded data and hide the threshold layer. And now our final result is our label image, and now each of those high density regions is a different color corresponding to a different label. So now if we hit this show selected, we'll get one of our clusters one at a time. Cool. So now we want to go back and actually add in properties for each of these labels, just the same way we did before, where we're going to sample each of our image layers for each of these labels, add it back in, and then look at it interactively. So let's go back to the notebook, and we will just, well, actually first let's rename this. So we'll call this high density labels. And I'll just go back and edit some cells to avoid having to copy paste. So now we get out of our high density values, and then the building the dictionary will be the same. We'll just replace our watershed array with our high density labels array, and run that, and then set our properties for our high density labels with the dictionary we just created. And now when we go back to plugins, clusters-plotter, look at this clustering. Oh, no, we don't actually want to run the clustering. Not yet. And look at our high density labels. We'll have now all of those values. So we can look at how the density actually changes across the label. And see that there's kind of a peak around 2.5, and if we select those, we'll get most of the values in the data set. And let's look at some of our other, so scatter plot, check out some of the other values. So temperature versus density, temperature versus, or metal density versus density. You know, we can go and select these down here, hit plot, and just pull out the four centers corresponding to that clustering down there. Check out the gas velocity as well versus density. And yeah, so that is kind of a nice way to just check out variations within just these high density regions. And then we can actually run some actual clustering too if we want. So if we look at our high density labels where we have all of the data, we can actually, you know, run a quick k-means calculation that'll use all of our variables here. The issue though with doing this right away though is that generally for these k-means calculations you want to scale your individual dependent variables so that when you're doing this, the k-means distance calculation, it doesn't overly weight variables that are on vastly different scales. So before we do that, we're going to want to recalculate our values. We also are going to rerun that last step and apply our labeling connected component. Okay, so now what we want to do is when we're building our properties dictionary, we'll just scale. We want to scale our result to the range of each image layer. So first off, we'll do this in two steps to be a little bit more efficient about this. So create a scaled layers dictionary, and then for each of these layers we want to sample. We will pull out the full data here, so not the label. Actually, let's do this in two steps. So let's first take the data and let's find the finite values. And then get the maximum value. Minimum value, and then Let's store the scaled array. So this will scale everything between 0 and 1. And then when we're pulling our properties, rather than pulling from our Napari image layers, we will instead pull from our scaled layers. And run that, and now our properties should be scaled between 0 and 1. Relative to the full values for all of the layers. So let's go and set those as our properties, and now go back to the clustering widget. Take a look at our high density labels and kmeans, and let's just run this with, I don't know, 4 clusters. See how that does. So what we get out is another properties dictionary. Now we have also, though, the kmeans cluster ID. So this is the cluster that it was assigned to. And if we go and take a look at our plotter, oops. And now when we select our fields, we can also select this kmeans cluster ID. And when we plot, now these colors correspond to the cluster that they were assigned to. So you can see that these actually do end up clustering together, these outliers here. Not outliers, but this low metal density but high temperature subset. Cool. So one kind of interesting application also, though, is to not impose this initial labeling of just the high density. So like if we want to say, for example, run a k-means clustering algorithm across all of the points in the images, there's not exactly a built-in way to do that, but it's not too hard to make it work. So we are gonna actually give that a go. So we're gonna simplify things a little bit. So we're gonna actually delete all of our layers and load in a couple more 2D layers. This time, though, let's use the isolated galaxy data set. And let's load some slices. Let's load in density. And let's keep this pretty small. And temperature, and let's just do the gas velocity magnitude. Great. So in order to just run a straight k-means classification on all of this data, we're going to do something a little silly, but works pretty well. So what we want to do is create a label array in which each pixel is its own label, so that when we run the k-means clustering algorithm with the clusters plotter, it'll actually pick up the individual pixel values and group everything for us. So that's why we switched to 2D, because in 3D it does not scale very well, and I would suggest rather running that classification in the notebook and and then loading back in labels. But for the 2D images, it works pretty well. Okay, so we have our different image layers that all have data size, a size of 36,000 pixels. So what we'll do is create a 1D pixels array for our labels that goes from 0 to number of pixels that we have. And we'll want this to be integer values. So let's make sure we enforce that. And then we want to just reshape this to be the same shape as our density. And since we're doing individual pixels, we don't have to worry about the contiguity of our nearby pixels. If we were trying to like group pixels, we'd have to be a little bit careful to make sure that when we're doing this reshaping, we're getting continuous blocks. But we can just reshape it to the same size. And then if we just do add labels, and then name equal pixel labels, we'll get out this crazy view where our individual pixels are all a separate label. So not great to look at, but it lets us do some fun clustering. So now we can go back and actually go and sample each of our layers at each of those values. We could do all this, but because we have those values already, because we don't have to take any means, they're single values anyway, we can just write a properties dictionary that is just has all of these values in 1D. So to create our 1D arrays, we will first want to rescale things again. So let's go ahead and do that. And we will just sample the fields we have, which is not quite as many. Get our scaled layers now, and then for each of these, in addition to scaling it, we can just unwrap it to be 1D. And now we can just have a properties dictionary where the label just comes from our 1D labels, and then our pixel values come from our just 1D scaled layers. And now we just have our 1D values for all these. And we can then go and add our pixel labels properties dictionary. Go back over to Napari, go check out the clustering widget, pixel labels. Now we have all of our fields. And so now we can run this kmeans on, and it will classify every single pixel here. And it's pretty efficient in 2D. It's not too bad. So we'll bump up the number of clusters just to kind of well resolve everything. And hit run. And we are done. So let's go take a look at the plotter widget. So now what we get out is let's first switch this just to a histogram, and apply that cluster ID, and hit plot. And so now this is a full histogram of the density values within our image, and then the cluster that they were assigned to. Temperature has much narrower range. It's kind of fun to, so if you look at these versus each other as 2D histograms, what you get out are essentially very similar to phase plots in YT. So these are straight 2D histograms, so doesn't do any of the sort of cell weighting averaging that a phase plot would do, but it's kind of a fun way to check out how your different fields are related to each other and distributed spatially at the same time. And so right now we're coloring by our cluster ID, and so this is kind of how the various fields got split up into their clusters. And again, you can select certain regions to pull out just those regions. And let's make this a little bit nicer. When you do a 2D plot as well, or 2D histogram, if you're not plotting by the cluster ID, let's switch this to a log histogram. There we go. You can apply color mass as well. So let's just take a look at these kind of low velocity, low density regions, get highlighted, and moving up. Cool. So that's pretty fun. Let's switch back to the kmeans. Cool. So that's actually like a pretty quick, nice way to run a kmeans algorithm on an entire on entire image layers using data from all the images. It's kind of a fun way to do things, and you can quickly check out how various features are distributed spatially. Yeah, so that covers about all I wanted to do for this video. Thanks for watching. This is the final video in the series for now. There might be some in the future, but this will be all that's coming in the near term. But definitely, if you have working through these and you have questions, feel free to hop over to the yt-napari GitHub. So right now it's hosted at the Data Exploration Lab GitHub, so data/exp-lab yt-napari. Feel free to open issues to just ask questions if you want, or come on over to the YT Slack and find me, and happy to answer any questions you got, or do some more videos for other features you might want to more details on. So thanks for watching, and that's all.